The last thing I'll say is that quite often I've been starting to see these getting used a lot more for probes, whether it's ground, the ground grid itself or just an individual rod. Understanding these tests, and we'll pop up a little thing showing this, is you have to understand that this only tests a loop. And there's so many different flavors. Right. Gregg has a different version of this, different manufacturer. But the thing is that the way these things work is you have two clamps inside of here, and one clamp injects a voltage, and then the other clamp measures the current that flows. And so it knows voltage divided by current. It can do its own math, and it can tell you, oh, well, I have a resistance of this. It's AC because it's induced voltage, so it has to be AC. So it means it's an impedance measurement. But this requires a loop in order to work. You can't just go up to one ground rod, clamp that thing on there and check it, right? That's failure mode all day long. The other thing about these is any test set that you ever have in the history of never ever, I've always recommended to go ahead and get the damn little thing out that says a calibration check. You put it in there. Yep, it says it's 5 ohms. You take it off. Oh, it says it's infinite. That means it's working right. So with the AEMCs or the 4-point testers, you can short all your leads together. You should get a 0 ohm reading. There's different ways of doing your functions check, but I always recommend get the low-hanging fruit out of the way, because if you run into an issue when you're testing, the last thing you want to do is just be like, oh, man, it's just a bad lead. I never checked it. It'd take you 40 minutes to find that problem. So just do a quick function check before you start.
Yeah. To build on this guy, because this is, if there was a controversial subject in ground resistance testing, this is it. And I've sat in many service managers' offices who are much more intelligent than I was, and they absolutely despise this thing because they had a bad time with it one time. And I think it helps to break down exactly how this works. And Tom's exactly right. There's two heads inside of here. They're electrically isolated from each other. One is inducing a voltage, which allows a current to flow. And the measurement is assuming that this voltage remains the same. It's constant. So we have a current that is returning. And how I always simplify this is to go back to that old adage, which we know is not exactly true, of charge is going to travel towards the path of least resistance, right? If we're attached to a grounding system that is bonded, let's say, to the utility, easy enough to picture that, right? We have a ground electrode conductor that's going up, that's making a neutral bond. That neutral is going out to the rest of the world, essentially. And there is a effective, solidly grounded system behind it that is, for all intents and purposes, infinitely sized and essentially 0 ohms. It's not 0 ohms, but it is essentially 0 ohms. So that's the way my current's going. My current's going out there, and it's finding all these parallel paths through the utility system to come back through my electrode system that I'm testing. Right now, it's a little bit more complex than that. As Tom mentioned, this is an AC. It's off frequency. Usually they're injecting somewhere in the range of greater than 1,000 hertz, usually 1,500, or like this one, for example of it, 2,000 hertz, or it's 2,078 hertz exactly. So as this test current flows out, it finds all these parallel paths. It returns back into the instrument. I have a voltage, I have a current, I have a resistance. We can break these down even further now. This one has an advanced mode. I can see what the inductive component is doing. Because I'm working at such a high frequency, I can do other stuff with this instrument. I can produce different values. Generally speaking, we see that resistance and our impedance are equal to each other. But now you can see some additional factors with your instrument because we see additional technology being built into these instruments that give you additional functionality. I think what's really neat about this one, and not a lot of people realize this will do touch voltage as well too. So when I clamp this on, I can actually get a warning if I'm greater than 50 volts. However, in the advanced mode, I can measure a voltage just by simply clamping it on to that ground electrode system. But it's critical to understand this is a loop impedance analyzer. We call it a ground resistance test instrument because that's what everybody thinks it is, right? It for all intents and purposes, it is. But it is a loop impedance analyzer and can be utilized as such. For instance, in the In the lightning protection industry, this is often used where point-to-point continuity measurements cannot be effectively performed. For instance, where a roof penetration is for a ground for the a lightning protection system on top of a high rise, for instance, I can't effectively measure that when everything is self-contained, but hidden, concealed within the building. I can now measure that because I expect to see that test signal looping through the system and returning back to the instrument. So a lot of flexibility in these instruments. Downside to this thing is that we're always taking it on faith a little bit. With fall potential, I'm taking multiple measurements. So if we're using this and we need to validate our measurement, let's look for additional electrodes that can be measured, and we should see some similar resistances. That's really where I think this instrument can be misunderstood, is that depending on where I'm clamping it is what I'm going to measure. For instance, if I have two ground rods that are next to each other, one's here and one's here, and I clamp below this bond that's interconnecting those electrodes, I'm measuring this electrode and this electrode, right? I get the individual resistances. However, in this example, if they're very close together, if I do just a simple parallel resistance calculation, that is not going to be the resistance of this system. These electrodes are too close. So be aware of what this instrument is and what it isn't. And this is why we see this instrument that is specifically not specified, or it is told in the specifications we cannot use this instrument, because it's oftentimes misunderstood. It is incredibly similar in its measurement capacity that a fall potential measurement is. Easier to deploy too, of course. It's just been kind of bastardized, unfortunately, in the industry because somebody had a bad experience with it one time and didn't understand it.